Good afternoon. I'm gonna speed through this presentation real quick that I had for my senior design to get my bachelor's in computer engineering. Um, I'm gonna speed through this. I'm not gonna watch the videos. I thought I recorded this earlier, but failed to hit record. So we're just gonna kind of breeze through this real quick. Um, anyway, I don't know if I hope I'm cool. Let me reshare my screen actually. That way I can set myself up. Uh yeah, here I'll go be part of the screen. I like that. Okay. Excelente. So this is a again senior design project with my team for a smart threat detection system using object detection. Oh, all right. These are the beautiful gentlemen involved. Miss you fellas. But yeah, had a lot of help. This is not a required part of the presentation or final project is a YouTube ad we made just to kind of highlight it. It was super fun, super goofy. Great editing, by the way, too. I never really appreciated it, but no, it's some good shit right here. Anyway, introduction. So approximately 5,000 burglaries happen on a daily basis, and one third of all these uh, burglaries and robberies result in injury, where about 40% of the time there's a weapon present at these. Um, Not to mention, since about 1965, weapon rates, the rate of arrests for illegal weapon possession um, have have doubled. So the objective of this project is to, of course, impact those statistics in a meaningful, positive way. And we're going to do this by designing an intelligent monitoring system that will enhance our ability to survey both public and private areas and identify various threats that could lead to security risks or bodily harm. And then our target audience is, in short, anywhere that you wouldn't want a firearm or a weapon. But these are not limited to, but include small businesses, homeowners, hospitals, schools, universities, churches, government buildings, airports, wherever you don't want a gun, we're there. So the proposed deliverables, the hardware that we used here was a Raspberry Pi 4 and a connected camera, a machine learning algorithm for the actual detection, and once an object is identified, we then send a text or alert notification to the appropriate authorities to for them to determine the course of action. We're merely an alert system, not necessarily um, I guess we don't take definitive action. We just inform. So here we have marketing and engineering requirements. We translate the market needs that we want our product to fill into how we're going to do that technically in the engineering requirements. And of course, you have a justification. I'd like to highlight the bottom row for the real time capabilities. This is going to be essential in most surveilling, monitoring, and alert systems. You need real-time reactions. You need real-time information. It doesn't do you any good if there's an hour-long queue of video frames to get put in, into this buffer and then analyzed an hour later. Well, by that time the damage has been done, and then you shoot me a text and alert saying, "Hey, there's a guy here." Well, no shit, he's been here for about an hour. So real time is key, and you'll see that the hardware that we use, because we're computing on an edge device, um, that is a significant hurdle that we have to overcome with this project. And what I mean by edge computing or edge device is as you move to the proverbial edge, you move closer to the source of data. You move the storage device or computational device closer to the source that's producing the data. In this case, so like a camera, right? A way that this could potentially work is a camera, just like any old security camera, has a photo, sends it off, sends the video stream off to a server. The server then runs, a machine learning algorithm, does this thing, identifies various objects in the frame, and handles all that server side. And then, but there's additional liability in the networking aspect. You have to worry about packet loss. You have to worry about network latency. You have to worry about, Wi-Fi to some degree, and signal strength. You have to worry about, then you have the whole slew of cybersecurity issues that come with using networks. So that's what I mean when I say edge devices, versus the edge device that just kind of handles everything in-house on the device. It doesn't get sent anywhere. But the crux with the issue with edge devices is typically you're not going to have as much computational power as you would with a whole server rack. So yeah, anyway, the marketing requirements need to be mass producible. We do this by getting easy, maintainable, and cost-effective parts. That way we lower the price point for people, for our target audience. Needs to be mountable and lightweight. Lightweight, sturdy parts that are wind resistant, water resistant. It can be mounted for long periods of time with little need for maintenance. Detect a variety of potential threats. Train a machine learning algorithm. Threats come in various forms. We have to abstract. Weapon identification or any object detection is a very abstract problem. So it just requires the flexibility of artificial intelligence. Of course, we detect threats at a distance. We're going to have a higher resolution camera in order to give the machine learning algorithm more pixels to work with, therefore leading to the best possible detection. And as stated here, poor resolution images are more difficult to decipher and can cause inaccuracies. We have the alert notification system, so we send a text message, and then we need to be able to distinguish between threat and non-threat. This is just based off like the data that we feed into the model. Then, of course, the most essential, the real-time tracking. Right, we use the Raspberry Pi for its real-time clock, its RTC capabilities, and then it's just essential as part of in a real-time environment where instant response is needed. A little bit about object detection. Object detection is to detect visual instances of objects within various classes in digital images. Okay. Yeah, object detection, fun stuff. Usually done with some sort of like computer vision or computer vision or something like that. All right, labeling. So part of the process of training an AI is you have to provide them with the ground truth. Okay, ground truth is a collection of pixels that you mark on an image, and you say inside of this box there is a region of interest. These pixels can be used for you to classify this type of weapon or rifle or whatever. So we went through, found a collection of weapon images on Kaggle, downloaded them. They were unlabeled. We spent time to hand label them and put bounding boxes around different classes: firearms, handguns, rifles, blades, things like that. We used about 5,000 images. And yeah, that was a lot of fun. Definitely painstaking. Here you can see I particularly like the variety of data that we had, because here the gun is upside down. We can see that any translation, rotation of an object just better allows the AI network to, what's the word I'm looking for? To generalize and infer what a gun is. The more variability we can introduce into the data set, the better it generalizes. Because if you feed it all pictures of a gun like this, it may think that a necessary requirement of a gun is for it to look like this. What if we invert it? Well, it learned that all guns are present like this, but without that rotation, translation, and flipping of images, it doesn't generalize well. But now, once we introduce both, it sees, hey, guns can come right side up, upside down, flip backwards. They can come all sorts. So maybe that's not a very valuable piece of information when distinguishing or determining what a gun is. You know, if I turn my head, am I still Xavier? If I turn my head, am I still Xavier? Okay, so then therefore my orientation shouldn't matter as much, you know, when determining who Xavier is. Just certain things can be their weight in classification can be decreased. Versus if I didn't have my glasses on, that's like, okay, that's a pretty important defining feature. We might struggle to identify him. Or if I didn't have my beard, you know, facial recognition may have a little bit more trouble. So it's just how heavily do you weight the characteristics, the variables in an object to best generalize what it is. And I find this just it's super interesting because we get into these ideas of language, the idea of a gun, the idea of a weapon. We think about that, we internalize that, we just know what we mean when we say that. But having to explain this concept to a machine, to almost a newborn baby, and getting it to understand the concept. Well, how do you do that? You have to teach it is at the most core fundamental level. What is a weapon? Could you tell me what core fundamentally makes something a weapon when they come in different shapes, sizes, colors, calibers? How can you reliably identify weapons? It's a hard question to fucking ask. It's a very difficult question to ask. So ultimately, what we do, we use statistics and algorithms to describe the concept in the best way we can to a machine, and I just find that so fascinating. Anyway, yeah, the ground truth. We say, hey, look in this box. You should find pixels here that you can use to classify. It finds like commonalities between all that, and then hopefully becomes reliable enough over enough iterations of data that things work out. And then we use the label IMG software. Yeah. Text notification, we send text messages via Twilio and automatically sends upon detection. This is done via frame counter. It counts how many frames that a weapon is on screen, and based off the frame rate, hence the real-time capabilities, which we'll get into even more later. But that's the necessity, is the frame counter counts how many frames a weapon is present for, and then boop, sends off a text message. Can be sent to any number of people, and it's a subscription based. They charge like 75 cents a message or 7 cents, I forget which, but easy to implement, just cool stuff. Preliminary design, of course, you have the outlet, you have the power adapter plugged in the Raspberry Pi, which needs to be connected to Wi-Fi for the text notification. And then you have images fed into a camera where which is then feeds down that input into the Raspberry Pi where the computation is done. You have the software flowchart, you have the input, the processing of the video, you acquire each frame of that video as an image, send that off for analysis, determine if it's a weapon. Yes, send a notification. No, then we just go fetch the next image or next frame of the video from the buffer. A little bit about our housing design. This is all 3D printed. It's biodegradable and it's capable of being mounted and withstanding pretty strong forces. Pretty strong is relative. It does its job. So a little bit about the frame rate, why it's so important. As I mentioned, it's essential in real-time detection capabilities. And real-time detection is very difficult with minimal frames. If I have a frame counter, okay, if I have a frame counter that counts how many frames that a weapon is present for, and the threshold is 300, I say a weapon has to be reliably detected for 300 frames. If I only have 1 frame a second, it's going to take me 5 minutes to get an accurate, to send off an SMS, which is a problem. I don't have 5 minutes. I need you to tell you immediately that something's going down. So, but if I'm getting 30 frames a second and that limit is still 300, guess what? That 5 minutes comes down to 10 seconds, right? Much faster. And it all depends on that frame counter and the amount of frames you get. The more frames that I can reliably analyzed in that time period, the quicker I can send off real-time messages and inform, the appropriate authorities or give people time to barricade or give people time to leave or it's just when you're in a situation where seconds matter, you want it to be as fast as possible. So edge devices reduce network latency. Um, it brings data storage closer to the data source. However, typically at the data source, there's less infrastructure to support large scale computation, whether that's power restrictions, like lack of computational power, things that like that, Um, I don't have time to bring a server or I can't mount a server rack to a wall. If I could and have like 64 GPUs all running, video analysis, it'd be crazy, but I can't. And then of course like let's say you're in an area that doesn't have like reliable connectivity to where I can offboard, that computation and send it via a network somewhere else for analysis. Let's say I'm in an area that doesn't have the infrastructure where we need that edge compute. We need that all done in-house. So that's some of the justification for performing this on edge devices. And ultimately, like I said, it affects the Twilio alert times as the message is generated off of the number of frames that a weapon is present. So how do we fix this? We implement a Coral USB accelerator, and this is a TPU unit. So you have CPU, GPU, and TPU. You got central processing, graphical processing, and then tensor processing unit. So tensors are high dimensional data. Okay. If I give you an image, what kind of data? That's two dimensionals. I mean, it's two dimensions, length and width. It's an array of length and width of two dimensions, and then it has pixel values along, the height and the width of each pixel, and the pixel is representative of the length of the array. Okay, so if I have a 4K image, it's gonna be I don't even fucking know. Oh, did I disappear? Okay. If I have a 4K image, it's gonna be 2000, an array of 2000 for the width, an array of 2000 for the height. It's gonna be those that in what it would be of length 2000 in both dimensions, is what I meant to say. It's not, yeah, it's not two separate arrays, but it's just an array of two dimensions. Um, And then so that's two-dimensional data. And then we get into multi-dimensional data. And this is where machine learning algorithms come in, where you could have data of multiple dimensions. And these are based off the input variables, right? So a dimension in this case would be, let's say I want to predict house price based off neighborhood square footage, crime rates in the area, color of the house. Each one of these things is a dimensionality of data. Okay. So I don't mean the data literally exists in the seventh dimension. I mean, there's seven factors, just like there's length and width. Okay. There are, in this case, four factors: color, size, location, and crime rates that all influence the price of a home, right? So we would say that a home price has the home price data or home price prediction has a dimensionality of four. Okay. These are higher order, these are just referred to as so like you have arrays, then you have matrices, and then you have tensors. Okay, and each one describes a different dimension of data, right? I forget, I think arrays are like, forgive me, this could be wrong. I should probably, you know what? Fuck it. I'll just Google it real quick. Let's Google it. I don't want to, because I don't want to be on here spewing this bullshit. Hold on. Array versus matrix versus tensor. I forget what makes, what level. I would say like an array an array is like 1 to 2 dimensions. A matrix is like 3 dimensions, and then a tensor is it. Okay, an array is an n-dimensional generalization of a matrix. Interesting. Interesting. A tensor is an n-dimensional array. Unlike a matrix, it shows an object's place in a specific coordinate system. Oh, whatever. Okay. Cool. Cool. Anyway, so yeah, let's say arrays are like 1 to 2 dimensions. Matrices are 3, and then whatever. Tensors are nth dimensional. But yeah, I think I was here. I forget where I was exactly. But oh yeah, then you have TPU, and this just allows us to do complex high dimensionality math. It's a hardware device specifically made to process high dimensional tensors. Hence hence its name and great performance with AI and machine learning models. The USB accelerator requires the use of TF Lite or TensorFlow Lite, which is a lightweight version framework, which is optimized for small and mobile devices. We use quantization in conjunction with the USB accelerator for further frame rate improvements, which I'll get into a little bit more about quantization later, and then hardware improvements. These hardware improvements mean upgrading from the RPi 3 Plus to RPi 4. So a little bit about the model. Use the SSD MobileNet V2 quantized version, which was originally changed on the Coco dataset and available via the I think they call it the zoo of models, right? SSD in this is a single stage detection model, hence SSD. The difference, single stage detectors go straight from pixels on the screen to bounding box coordinates and class probabilities, whereas two-stage detectors have a sparse dense uh, network in their architecture, okay, and they determine ROIs or regions of interest and then perform regression on those regions of interest. Whereas single stage detectors generate thousands of candidate boxes, perform regression on those, and then the bounding boxes that are ultimately displayed on screen have the highest correlation or highest class probabilities, you have TF Lite, which is compatible and quantizable. Hence the model. The reason we chose the quantized model is able to be quantized and is optimized for mobile devices. As a two-dimensional convolutional layer, I'm not entirely sure what this bottom point is trying to make. It's been so many years since I looked at it, but anyway. The quantization of the model. So first you start off with a very large full-size model. You scale down to TF Lite, which removes some of the available operators, but ultimately makes the model simpler. And then we move finally to the quantized version. Quantization is the act of constraining an input, okay? Quantized models use lower 8-bit precision inputs as opposed to floating or double data type counterparts, okay? So for those that don't know, you have different data types in computer. You have different data types that you use in a computer, right? So you have integers, which are typically are represented by 8 bits. So you are able to represent 256 total digits, all right, from the range of 0 to 255, and it's done on a binary basis, okay? So you use 8 bits that you turn on and off to represent various numbers from 0 to 255, all right? Now, they have different data types which allow higher degrees of precision, such as floating point values or double values, okay? Floating point is usually 32-bit precision. It's 32-bit precision values, and they can represent massive numbers and super fine like fractions down to like the millionth, billionths, trillionths. Um, I would have to go. I have it somewhere in my notes, like the range of numbers that you can represent with floating point values, but the level of precision that you get when you can represent something with 32 bits versus 8 is the difference between quantized and unquantized models, right? So naturally, the precision that I get is lessened with 8 bits, but the computational resources required to do 8-bit math versus 32-bit math is extremely like varies extremely. The performance requirements needed there. So 8-bit, ultimately, you lose precision, which causes you to lose accuracy in the model. Okay, it's less it's less reliable. However, the speed that you gain in this case, in this real-time format, is able to be sacrificed, in my opinion. You have here you have a formula. Sorry, fucking roommate. You got a here you have a formula that tells you how the quantized value is calculated. And of course, you can do some algebra here to derive the int8 value from the 64 32-bit original. TF Lite only supports certain ops with restrictions to how models can be quantized. You can apply quantization on a per tensor or per axis basis. So each one of these tensors, each one of these neurons, okay, can be quantized individually, or you can get a value for this entire axis and quantize once. It depends on how much speed you want and how much accuracy you're willing to sacrifice. We quantize on a per tensor basis. Needed for edge TPU core devices and a faster frame rate. Like I said, quicker computation to be done. Pair that with the edge TPU. Now we're getting some serious frames. I'll skip through these momentarily. Societal impact, this technology, depending on where it's used, has may have the ability to impact concealed, open, and constitutional carry states. So that could be, of course, we're looking at moving people out of the face of danger. So will have an impact on safety. And then you have the technical impact of advancements in video analytic technology and allowing algorithms to learn and adapt to new threats is great. The weapon detection system allows for a security system to be proactive versus reactive. And you also have real-time weapon detection that's never been implemented in conventional home and small business security systems before. This is part of the project. We had to compare product comparison, why we're good, why we're, market analysis, what will we charge, how we do this, and stuff like that. Not gonna get into that too much, but the crux of this was we're the only one with weapon detection. Got a timeline, some codes and standards that we abided by. We have the demo. I'm not gonna watch that right now. It's just me holding up a bunch of guns and watching it detect and then getting text messages. So in conclusion, our design identifies active threats by revealing displayed weapons. Notifications provide time for action to be made to minimize casualties. Then artificial intelligence detection system will impact many people, from universities and church organizations to businesses and homeowners. Questions? Yeah. Got some backup slides. So some of the future plans and future work, we would love to use infrared and thermal imaging cameras that detect concealed weapons, better cameras and higher resolution images to increase detection distance, and then also implementing some sort of clothing or person recognition in the software. That way, once something is, a weapon is detected, whether it's concealed or out, we can send part of the text message will include a description of the person, or we track, it's able to track the potential threat. Here you have the pricing structure for Tulio, super cheap, like a cent or two is less than a cent. It's super easy. Part summary, um, acceptance criteria, yeah, needs to be mountable, needs to send a alert notification, and needs to be able to reliably detect from a distance. Assumptions and constraints, Right now, the weapon does have to be displayed. Threats must be within the camera's view. There's a stable power supply, and any Wi-Fi security or things of that nature would have to be handled by the third party purchasing the device. Constraints, it has to be mountable, so it may not be able to survey as wide of an area if it could be moved. Camera resolution affects detection and accuracy, so we're constrained by the resolution. And then limited frame rate of the Raspberry Pi camera, um, could hinder our real-time capabilities. So we use about 70 to 80% of the data of that's 5,000 images for training, 20 to 30% used for validation and testing, and then tweak the model and optimize accordingly. We use data collection and pre-processing to expand the possible data that we trained with. Some of this included cut mix, mosaic data augmentation, translation, flipping, changing colors of images, things of that nature. These general help allow the model to generalize the data that's present in these images, because it, instead of gathering 15,000 images, we gathered 5, but then rotated all of them 90 degrees and generated another unique 5,000, then rotated them another 90 and got a new 5,000. It just allows for data to be used repeatedly in a way that's just efficient. You have references, and of course, this is the executive summary if we're just delivering that to a really short audience, but that's about it, man. Hope you guys found this intriguing. I will put out some new videos here soon. But I have to, these are pre-made slides. I'll have to actually go through, make the slides to go through, new, not, my next video is probably gonna be like deep learning 101, bunch of definitions, explanations, stuff like that. But I gotta go slap all that on slides. Hope you guys found this interesting, and talk to you next time.